Hello guys, this is Justin Bibilan and welcome to this episode of Don't Panic, It's Organic.
Okay, our next topic would be about reactions involving benzene. Okay, for these reactions, I will only be talking about the basic reactions involving benzene. So I will not anymore go deeper because this is just only a general basic uh, subject, okay, course, which is actually a general organic with biochemistry. So I will not go deeper on reactions like Friedel-Crafts, acylation and alkylation, and also the meta-directing and auto-para-directing activating groups and the activating groups. So I will not discuss that, but for that is only for Chem 104. Okay, because that for Chem 104 it's only basic. But for major in organic chemistry, the BSEDSCi11, I will actually make a separate video of reactions involving benzene, which actually contains the more detailed on mechanisms for reactions involving benzene, and also the Friedel-Crafts acylation, alkylation, and also the meta-directing and ortho-para-directing the activating groups and activating groups. Okay, but this is for Chem 104. This part here is for Chem 104 only. Okay, so the reactions involving benzene is actually governed by what we call an electrophilic aromatic substitution or EAS, electrophilic aromatic substitution. Okay, your benzene is a very stable structure, has a very stable structure, attains its chemical stability. However, it's actually rich on electron because of the electron clouds. Okay? Okay. So, therefore, we need to have an electrophile. Okay. Electrophile is needed. So, when you say an electrophile, it's actually an electron loving. Okay. So, in order for a benzene to be activated for a further reaction to proceed, an electrophile should be generated. Okay, so that your benzene should be activated. Remember, unlike alkenes, benzene plus other aromatics do not generally undergo addition reaction. Okay, they are not really undergoing addition reaction. Okay, like alkenes. So there should be what we call an electrophile, which is what we call an electron-loving substance. Okay, it could be your Cl2, which actually being turned to be transformed into an electrophile, and the result is a substitution instead. Okay, your hydrogen that is actually found on a benzene will be substituted with an electrophile. However, this reaction should be facilitated with a Lewis acid catalyst. So when we say a Lewis acid catalyst, a Lewis acid is an electron pair acceptor. Okay, remember that, for example, your halogens, they're actually rich on electron pair. Okay, so this would be accepted, or the electron pair will be donated and accepted with your Lewis acid. It would be donated with your halogens, and it would be accepted with your Lewis acid. And therefore, one of the Cl would be attached to your Lewis acid. For example, if it is a Cl2 or a Br2, one of it will be attached to your acid. Then the formation of an electrophile will result. An electrophile is actually a positive, or it's actually a cationic in a structure. Okay, it's a positive charge substance or atom. Okay, so because it's a positive, then it actually tends to love electrons. Okay, it's actually seek electrons, which actually rich in benzene because you have an electron cloud that is a very rich in benzene. Okay, so these reactions are facilitated with the Lewis acid. Then the key reaction pattern is what we call an electrophilic. You have an electrophile, aromatic, which is a benzene substitution. Okay, so for example, if you have a benzene, then you have your electrophile. Then it's facilitated with the Lewis acid. And that electrophile will substitute your hydrogen. And that electrophile will be attached to the benzene. And you have your bonds form. You have your CE, okay, which is actually a catalyst, and your E, and also your CH. Which are actually bonds broken. Okay, so for our first electrophilic aromatic substitution is the addition of your Cl2 or Br2 with the Lewis acid catalyst. Okay, so how is it done? So if you have your benzene plus Cl2, so the Lewis acid catalyst would now be your FeCl3. Okay, so this is now your Lewis acid catalyst. Okay, your FeCl3 will bind, your Cl here is actually rich in electrons. Remember that it is an electron pair. So one of the Cl will actually bind with your catalyst, and the Cl left there is actually, the result would now be an electrophile. So one Cl, the result is actually an electrophile, which is actually Cl+. And if this is already an electrophile, then the electrons rich in benzene will attack your electrophile, because this is actually rich in electrons. And therefore, the resulting product would be your Cl would now be attached to your benzene, and therefore this hydrogen will be removed. Okay? So you have your formation of your chlorobenzene. So that H would now be substituted with your Cl. Okay. It's also the same with your Br2. Okay. What's the difference is that only your Lewis acid catalyst. Okay? If your electrophile is a Cl, then your Lewis acid should be FeCl3. If your electrophile is a Br, therefore your Lewis acid catalyst should be FeBr3. Okay, so the formation of this with the formation of an electrophile, which is a Br+. Okay, you have your Br+, and your benzene, which is rich in electron, will attack the electrophile to form your bromobenzene. Okay, easy. This is only basic. Okay, when the second equivalent of the halogen is added, then 3 isomers are formed. That is correct. Okay, so for example, what are these 3 isomers? You have your ortho, meta, and para. So for example, if you have already a bromobenzene, okay, you have already a bromobenzene. Then if you are going to add another Br with the presence of your Lewis acid catalyst, then the formation of your electrophile will result. Okay? Then your benzene will attack this electrophile. However, you will have several result or product which have actually 3 isomers, because your Br can attach here, your Br can also attach there, and your Br can also attach there. Okay? So that you will have an ortho dibromobenzene, you have your meta dibromobenzene product, and you have also para dibromobenzene product. Okay? Then don't forget your HBr. Okay, next reaction is what we call the sulfonation of benzene. This is actually done using an oleum. An oleum is a Latin word that is actually variations of sulfur trioxide in concentrated sulfuric acid. Okay, you have your variations of sulfur trioxide in concentrated sulfuric acid. That is what we meant by oleum. Okay, so when oleum is actually present, then therefore this is what we call a formation of an electrophile, which is which becomes an SO3H. So this is an SO3H, and you have your sulfur as your positive. That would be the formation for this oleum reaction. You have sulfur trioxide in concentrated sulfuric acid. You have the formation of this electrophile, and this would be attacked by your benzene to form your benzene sulfonic acid. Okay, so the product for the sulfonation of benzene is a benzene sulfonic acid. Okay, remember that. The product for a sulfonation of benzene is the formation of benzene, sulfonic acid, and your water. You have nitration of benzene. Very simple. You're adding nitro to the benzene. So the reactants are nitric acid in concentrated sulfuric acid. You're heating it only at about 50 to 55 degrees Celsius. Okay? So in this case, we can actually form nitro, which is actually an electrophile here. So a nitric acid in concentrated sulfuric acid will actually form an electrophile, which is a nitro electrophile, and this will be attacked with your benzene to form your nitrobenzene. Okay? Very easy. So that's it. Those are just some basic reactions involving benzene. Remember those? You have your electrophilic aromatic substitution of your Cl2 and Br2 with your Lewis acid catalyst. So if you're adding Cl2, then your Lewis acid should be FeCl3, so that your Cl would substitute your hydrogen from the benzene to form a chlorobenzene. And if you're going to add Br2, then your Lewis acid catalyst should be FeBr3 in order to form a Br electrophile, which in turn be substitute your hydrogen from the benzene to form a bromobenzene. And you have your sulfonation of benzene, which is actually an oleum. So an oleum reaction would proceed and will form an SO3H electrophile, which in turn be attacked by your benzene to form a benzene sulfonic acid. And you have your nitration of benzene. You have your formation of a nitro electrophile, which will in turn be attacked with your benzene to form a nitrobenzene. Our last topic for aromatic hydrocarbons is what we call the heterocyclic aromatic compounds. So what are heterocyclic aromatic compounds? These are actually compounds with have at least one atom other than carbon as part of the structure of the aromatic ring. Remember your benzene? Your benzene, all of the structure there are actually carbon, 6 carbon. If you are going to substitute or replace one carbon with another atom like nitrogen or oxygen, then that is what we call an heterocyclic aromatic compounds. Okay? So example of these are this one. Remember your benzene? So if one carbon, you have at least one atom is replaced. Okay? One carbon is replaced with another atom. Okay. So this pyridine here, so this is what we call the pyridine. You have one N. Okay, you have your aromatic ring. So one carbon there is actually replaced with nitrogen. Then therefore that compound is what we call a pyridine. If two carbons are replaced with 2N, that is what we call a pyrimidine. If this is a complex now, you have your purine. Okay. As a purine, you have your imidazole. You have your furan that is actually replaced with oxygen. And you have your perol. So these are example of heterocyclic aromatic compounds. You just have to familiarize this heterocyclic. Okay, what are these important for? So your pyridine, okay, pyridine is actually found on where? It's actually found on the structure of nicotine. Okay, nicotine contains a pyridine structure which actually responsible for its addictive part. Okay, mostly nitrogenous compounds, organic compounds are actually are the ones responsible for what we call addiction. Okay, so pyridine or it actually nicotine contains a pyridine structure. Okay, how about your pyrimidine and purine? Where do you get this? Or where do you find pyrimidine and purine? They're actually found in your DNA and RNA. Okay, your deoxyribonucleic acid and your ribonucleic acid. These are actually nitrogenous bases which are actually found on your DNA or the genetic material. Okay, pyrimidine and purine. Okay, they are nitrogenous bases found on the DNA and RNA. Okay, imidazole. Imidazole is actually found on the structure of cimetidine. Okay, not that. Cimetidine. Okay, Cimetidine is a drug, or it's a drug that is used to treat ulcer. So it contains an imidazole structure. So that's why those that are actually used to treat ulcers, hyperacidities, are actually has a sol or zole on its a name, like your pantoprazole. What are other prazole? Imidazole. No, no. So there is also another pantoprazole. I forgot the other names for those that can treat ulcer. So they actually end with zole. Okay? Isoprazole, there's also an isoprazole, and also on and so forth. Okay? So they actually ends with OL. OLA or OL. Okay? Your pyrrole, your pyrrole is actually found on is one of the components for the structure of your hemoglobin and also the chlorophyll. Okay? So your hemoglobin is actually you have it's actually the structure is what we call a porphyrin molecule. So your porphyrin molecule is contains a pyrrole there. So this is a pyrrole, that is polypyrrole. So there are many pyrrole that are present. Okay, that is attached with your iron. That's why your hemoglobin or your blood contains an iron because of the presence of hemoglobin. And this iron there is actually being stabilizes or being what we call there's a coordination bonds with your or coordinated bonds with your pyrrole. Okay, pyrrole molecule. Okay, if your Fe3 plus is substituted with Mg2 plus or magnesium 2 plus, then that is what we call the chlorophyll. Okay, so if this is Fe3 plus, then therefore that is color red because of that would be the color of our blood. But if it is magnesium, then that becomes green. Okay, that is actually the color of the chlorophyll in plants. Okay, and this is the structure of cimetidine. You have your imidazole structure there. Okay, this is used to treat ulcer. I think that would be the last topic for aromatic hydrocarbons.